We're going to end this unit with what should be a really easy skill if you've understood what we've done so far. If you're struggling with writing these configurations, then you need to go back to your old notes, go back and watch previous videos, and relearn how to do orbital electron configuration and noble gas notation. Because while today's skill is really very simple, you can't do it unless you can write a configuration. If you take a look at oxygen, our F5 set up our orbital notation here. These electrons have two different sets of names. Some are called, as we look at our cheat sheet here at the very back, some are called inner shell electrons, some are called valence electrons. Again, go ahead and look at the bottom of the back of your regular cheat sheet, and you'll see the last section we haven't gotten to titled valence electrons. The reason that we go through the trouble of designating these two different types of electrons, on the board they all look the same, right? We've just got 8 arrows here representing oxygen's 8 electrons. But I'm going to be annoying and go even further and say that you need to know that some of them are valence and some of them are not valence electrons, called inner shell. But here's why it's a big deal. If I were to draw an atom with the nucleus there in the middle, all right, what are these guys right here? What are they called? Orbitals. All right, remember the orbitals are where the electrons exist. And I were to draw some electrons, all right, that's oxygen. Do you see how that kind of represents oxygen? Look what I've done. Look what I've done. How many electrons did I draw? I drew 8. Oxygen has 8. I put 2 on that very first energy level. And while this one circle doesn't completely properly represent how the orbitals are set up for that P, it still shows that in the second energy level, there's 6 total electrons sitting there. The most highest energy electrons are the valence electrons. If we go back to our orbital configuration here, and we identify what the highest energy level is, it's the number 2. Now, this could be a much longer notation, as we know. It can go on a long ways. But to identify which has the highest energy, and to have the highest energy, it's going to be those furthest from the nucleus. You just have to find the biggest number, which is really simple for a second grader. So we should be in pretty good shape. And once you find the biggest number that you've written in your configuration, you just got to account for the electrons there. In oxygen's case, we just looked at the big 2 and said, well, there's 1, 2, 3, 4, 5, 6 that exist with the big 2. Therefore, oxygen has 6 valence electrons. 8 electrons, but 6 valence electrons. 6 in the highest energy, furthest away from the nucleus. Why does this matter? Well, this is going into our next unit, so this next thing, don't write this because you don't need to know it yet. But just some food for thought. The reason that we really care which electrons are valence and which are not is, what if 2 oxygen atoms were floating near each other? All right, let's say these are 2 different atoms of oxygen in space somewhere that are floating towards one another. Do you see why the valence electrons are the ones that are really going to matter when those 2 oxygens meet each other? They're the electrons, they're the part of the atom that are going to connect first, that are going to dictate the way that the oxygens will interact with each other, and as we see really soon, bond with each other in order to form compounds and stuff. We're going to be obsessed with valence electrons in here for the rest of the semester because of this basic setup here. Anytime 2 atoms come near each other, the only interaction that they have are the electrons on the outermost orbital, the valence electrons. Our job today is not to know how they interact. We're going to do that in November. Our object today is just to be able to count them, and it should be very simple. Any questions so far? Now, The only other skill, and we're going to practice a few of these to make sure that you can count them, but you'll be good at it. The only other thing we can do with this information, that oxygen has 8 electrons, but only 6 of them are valence, is look at the back of this sheet. Look at the other side of your secondary cheat sheet. And you'll see that there is more data back here that I'll be reading off of. And what this is another funny little pictorial way that we can show the number of valence electrons that an atom has. These are called Lewis dot structures. Now, before we draw oxygen's Lewis dot structure, that's oxygen. Look at this. I'm going to draw a box around oxygen. Kind of looks like it does on the periodic table. We're going to represent these valence electrons using dots, but the basic thing I need you to understand is that the element has 4 different sides that you can put dots, with a maximum of 2 per side. Listen to what I just said again. An element, if you imagine a box around it, you won't draw the box, but imagine that it's got 4 different sides that you can put some dots to represent the valence, and you can only put a maximum of 2 per side. What's the maximum number of dots you can put around an element? What's the maximum total? 8 would be the total, right? 2, 4, 6, 8. So with that in mind, in your notes, this should be probably the first thing you've written. We're going to draw what's called the Lewis dot structure of oxygen. And it's real simple. Bless you. Pause. The dots you're about to draw only represent the valence electrons, which means you're not going to go and draw 8. Oxygen does have 8 electrons, but 2 of them are inner shell, while the other 6 are valence. And here, watch how this works. Remember, imagine that box. 1, 2, 3, 4. How many more do I need to draw? Just 2 more. Remember, we're drawing the valence electrons. 1, 2, 3, 4, 5, 6. The electrons in the highest energy level. 5, 6. Now we're going to do another one from scratch in a moment because this kind of feels disconnected right now. But in a nutshell, the lesson's dedicated to this. Draw the notation, identify the highest energy level. That'll give you a total valence count. And then you can take it a step further and draw a dot structure. Find zinc on the periodic table. Zinc. Somebody tell me how many total electrons zinc has. 30. All right. I want to do the electron configuration notation. Electron configuration notation. Which one is that? Was that the one with the exponents, right? 1s2, 2s2. The one that goes like that. So let's say, though, that my question is, what's the Lewis dot structure for zinc? Listen again. My question is, what's the Lewis dot structure for zinc? Well, that means that the answer is going to look like this. We want zinc with some dots around him. We just don't know how many. So let's do the electron configuration notation for zinc. You should be writing what I'm writing. We always start at 1s. Use all the references that you have available to you. 1s has 2 squares. Stop me. If any part of the configuration confuses you, please stop me. 2s has 2 squares. After 2s comes 2p. How many squares does p have? He's got 6 squares because he's got those 3 orbitals, each holding 2 electrons apiece. After 2p comes 3s2. After 3s2 comes 3p6. Now remember, we're trying to get to zinc, so our exponents will need to equal 30. Or you can go see that zinc lives in the 3D block. After 3p6 comes 4s2. What comes after 4s2? 3d. Now, 3d is zinc's location. Verify it. Let me know if you don't see that. All D blocks have 10 elements in them, so the biggest number we could put there would be a 10. How many elements over is zinc? Yeah, he's the very last one, right? In the 3D block, zinc is the 10th element. And now if you add up all my exponents, it does equal 30. But unfortunately, that's not what we were asking. Remember, we want to know the Lewis dot structure of zinc, which means we need to know how many valence electrons zinc has. So make a decision. Look at his configuration. I want to know first, how many valence electrons do you see in that configuration? Don't answer out loud. How many? 2. The correct answer is 2. And here's how easy it is to see that it's 2. Watch. To find the valence electrons, we need to identify the highest energy level. The energy levels are the big numbers. There they are. These are all the energy levels in zinc. What's the biggest number that I circled? There he is. The biggest number I circled is a 4. Hey, sometimes there's more than one. We saw that in oxygen. Are there any other 4s that I circled? Not in this one, but make sure you check. So this is the only 4, and how many electrons are existing in that energy level? 2. We've got 2 valence electrons in zinc. That still doesn't answer my question. My question is, what's the Lewis dot structure of zinc? How many dots do we draw? 2, right? Feels very obvious. The dots are simply 1 dot for every valence electron. Sir, do you have to start on top? I don't care where you start. Just put 1 dot on each side before you double them up. But there's the answer. Now, to get to that answer, we had to do a lot of work. So don't let the shortness of the question trick you. All I asked was, what's the Lewis dot structure of zinc? But I had to do a bunch of stuff to figure it out. Questions?